The title of this presentation is Visualizing de novo genome assemblies with Bandage. To begin with a presentation overview, we'll be describing Bandage and its input parameters. And this is a bioinformatics application in which it takes as input FASTA files from genome or transcriptome assembly pipelines. And then within each one of these FASTA files, which can be used as an input file, the file itself consists of a collection of genetic sequences which have conserved motifs, introns, and exons. And we'll be discussing motivation for looking at bandage graphs as a proxy for sequence quality that we'll be explaining and how we can visualize how different sequences are approximated and probabilistically computed with these assembly algorithms from either the genome or the transcriptome. And then to inform our discussion, we'll be providing several examples of graphs generated within the Bandage GUI. And there's also a way to be able to implement Bandage in the command line, but for our beginning purposes, it's easier for people who are just getting used to this or just starting out to be making use of this in terms of the graphical user interface, which allows someone to directly input the FASTA files into the application. So Bandage is a bioinformatics application, which stands for a bioinformatics application for navigating de novo assembly graphs easily. And there's some documentation that you can look up on the internet on Google from different types of applications and uses of Bandage. And then in the documentation itself, the people who developed this platform, they describe different sample data for which they use to construct different graphs like the ones that we're going to be discussing, in which they look at making use of an E. coli assembly, as well as looking at a transcriptome assembly pipeline for the mouse from Trinity. So we're going to also be looking at and making use of some type of possibilities from a Trinity transcriptome assembly pipeline. And I'll be discussing how this makes use of different types of purposes and use cases and interpretations that Bandage can help us with. So besides this introduction about what Bandage is, what the acronym stands for, and what the type of application it can be, applications would be of good use for it, we can look at further exploring additional applications of Bandage. And this is given by the fact that we can input a FASTA file from the Trinity transcriptome assembly into the Bandage application. And then once we actually, once the FASTA file is processed for however many sequences are contained in the FASTA file, the Bandage application is able to output and provide some type of information about how many, various characteristics of the graphs that it includes. And I've included two different types of examples that we're going to be discussing throughout this short presentation, and how they reflect different qualities and characteristics that Bandage can make use of. First of all, whenever we're constructing a graph from the transcriptome assembly FASTA files, we can look at the node count as well as the edge count, and then how many edges overlap, as well as the total lengths and base pairs of the overall number of sequences that are contained in the FASTA file. In the first case, on the left-hand side of the slide, we see that we have around almost 20,000 nodes for one of the examples, as well as around 1,800 edges, as well as no overlap in the edges in all of the graphs that are constructed from Bandage, as well as a total length of approximately 7.5 million base pairs. And then from this, besides the characteristics of the graph assembly that Bandage constructs on the left-hand side, on the right-hand side, we can also see that there's a node count of around 270,000 nodes in the graph, as well as an edge count of almost 231,000 edges, as well as the graph consisting of approximately 63 million base pairs. So there's a pretty large difference in the base pairs, in the total number of base pairs of one Bandage graph assembly on the left in comparison to the Bandage graph assembly that's constructed on the right. And we would like to see whether there are any different types of interesting qualities of these graphs that can help us determine how probabilistic computation comes into play when we're running transcriptome assembly pipelines, because inherently in either transcriptome or genome assembly pipelines, there's some degree of uncertainty in how the algorithm can generate the total length of the sequence, as well as other additional smaller fine-grained components that are also included in each one of the sequences. So we're going to be looking to the graphs that Bandage is able to construct, this bioinformatics application, and how it reflects uncertainty of the algorithms in constructing different sequences or potential candidates for sequences. So when someone loads in a FASTA file into the Bandage GUI, and after you draw the graph, you can look at a total ensemble of graphs and collection of graphs, such as what's shown here. And to begin our discussion, I've deliberately zoomed very far out in the ensemble of graphs that we have, because we can see that more near the top, there are some graphs that have some maybe more irregular shapes of the types that we'll be discussing in examples, as well as from the fact that there are many other graphs below the ones on the top that are just mostly consisting of lines. And we'll be discussing what's the difference between graphs that either have lower degree or with the graphs that have nodes that are either of lower degree or higher degree, and how this reflects uncertainty in the probabilistic and other types of computational methods that are used in the transcriptome assembly from Trinity. And this is just from the first example that we provided information on in the previous slide on the left-hand side, in which the total length of all of the graphs that is included in the sequencing has around approximately 7.8 million base pairs long. So we can input this FASTA file, and then there will be a collection or an ensemble of graphs that will be in correspondence with whatever the total number of base pairs is in the sequence, and then we'll be able to form interpretations from whatever FASTA sequencing file we provide the algorithm with. And this is just to show from a first example. So from the previous example, if we look at the total of the collection of graphs that Bandage constructs, we can look at different types of candidate graphs, which is any one individual graph within the entire ensemble of graphs, and what the characteristics of this graph would be, and how this reflects on qualities of the sequences that the Trinity transcriptome assembly procedure outputs. In this case, we can see that for the first item that I've indicated is that there are some graphs which have, or some components or pieces of the graph which have linear segments. And in Bandage, there are settings that someone can use either within the GUI or in the command line to label each one of the segments of the graphs. In this case, we can see that the segment 58C021 as well as 58C015 are both consists of what I call linear segments, as well as other segments which I've given from other labels in the graph, which appear more to the left hand of the slide, which consists of forks. And when I mean forks, I mean the terminology that I mean by that is that when there's a bifurcation, in which you can see that at the beginning of the graph that's assembled by Bandage, 58C00 is consisting of a linear segment, but there's a bifurcation in which there's a degree 2 vertex in the graph, in which there's a separation from the segment 58C00 into two other segments, 58C01 and 58C02, which consists of different base pairs from the sequences which are approximated by the Trinity transcriptome assembly. So these forks, as well as the linear segments of the graph of the graphs that are constructed in Bandage, and in particular, which are shown in this example, demonstrate to us that there can be different types of sequences from the transcriptome assembly, or different types of assembly procedures that generate FASTA output, which can overlap with some number of base pairs, which is given by the contents that are included in the 58C00 segment, but then they can diverge and differ before coalescing together and having some different types of base pairs predicted by the transcriptome assembly algorithm. So this is just demonstrating one possible example that demonstrates to us how different components, depending upon the degree of each one of the nodes or vertices in the graph, can help us interpret and look at different types of sequences and candidates for sequences that are produced in the FASTA file from a transcriptome assembly. Besides this first graph example, there's also a second graph example, which generates many similar qualities as to what I mentioned in the previous slide. There can also exist some type of linear segments, as we've been demonstrating, which in this case, the overall topology and the overall structure of the graph differs a little bit, in the sense that we have linear segments at 24C00 as well as 24C03, but there are a different number of forks that are interspersed at different positions of the graph. We can see that in between the segments 244C09 as well as 244C012. There are two there are two vertices, which are separating these forks, these forks which appear in between these two segments, as well as other forks which appear in between the segments 244C09 as well as 244C06. And the same observations apply for other graphs in the ensemble, in which, depending upon the sequence and the sequence that's predicted in the transcriptome assembly or in the genome assembly, if you're interested in looking at Bandage for genome assembly, there can be a different distribution of sequences or of base pairs in the sequence which overlap, and then there can be different distributions of forks throughout the Bandage graphs that are constructed. But besides the first example, in a few graphs that we were looking at to demonstrate some qualities of the fastest sequences that Bandage can help us look at, we can also look at a second graph assembly. And recall that this graph assembly differed from the previous one in that it was consisting of approximately 63 million base pairs in comparison to the first one, which had approximately 7.8 million base pairs. So this graph assembly, it's undoubtedly much more complicated, around almost 9 or 10 times as many base pairs as the previous sequences contained in the first FASTA output, which can probably give us some type of more rich interpretation of the graph structure and what this is reflecting of in terms of the sequences that we're looking at. And we can take a closer look in the assembly, and we can observe just this observation that we just mentioned, in which there can consist of many types of graphs, and they can have a higher node count, which is reflecting that there's a higher probability of having more sequences in the FASTA file from the transcriptome assembly and Trinity, which overlap. But not only this, but that there can also exist more differences or more variety in terms of how linear segments and forks are distributed in terms of each one of the possible candidate graphs that Bandage can produce for our studies of the transcriptome assembly pipeline. And for our first example graph from the second transcriptome assembly procedure, we can see that there is a commonality from the fact that there are linear segments which are included in some ending segments of the graph, which consists of one of which is 5643C01, but there can exist a more complicated graph structure from this that's generated from the bioinformatics pipeline, because there can exist forks on forks. And what I mean by forks on forks is that there can exist some vertices, as we see here in this cluster, which consists of some vertices which have degree greater than 1. And within any one of these segments which have a degree greater than 1 vertex, there can also exist other vertices which have degrees greater than 1, which are further branching off and demonstrate further complications and further possibilities for different sequences that are generated from the transcriptome assembly procedure. But besides this first example graph, a second example graph is also very interesting because it's demonstrating what we can describe as an inner cluster consisting of forks on forks. We can see that for the most part, the outer segments of this example graph that we have on the slide consist of linear segments of nucleotides that are produced from the Trinity transcriptome assembly. But in the middle part of the graph, there's more degrees. There's more nodes of the graph which have higher degrees, and they almost form a cluster, which is consisting of different possibilities for the middle parts of the sequences, and which can help us combinatorially realize and interpret different possibilities for many of the sequences which are generated by the transcriptome assembly. And within Bandage, there are additional functionalities which include building a BLAST database and querying for sequences, which shares in similarities from the NCBI command lines, which are open source, which one can use, such as BLAST-P, BLAST-N, and BLAST-T, to help determine other types of sequences which are similar to a given input to the sequences in a given output file, which lie within a certain expectation parameter that these algorithms make use of. So in terms of conclusions, we describe applications of Bandage, including loading in FASTA input for interpreting sequence quality, in which, like how we have been saying, if there is a graph which is completely, which consists of a linear segment in which all of the nodes in the graph have degree 1, then that implies that there is no uncertainty in this graph, or there's no sequences in the FASTA file which share in some nucleotides or base pairs of the graph. But this is a rather idealistic case, because as we can see in many cases, there are graphs which consist of nodes, many of which have degree greater than 1, or even can have degree 3, 4, or 5, as we had demonstrated in the graph example, which has an inner cluster approximately near the middle of the graph, which can generate, or which can indicate to us different types of uncertainty that we can expect when comparing sequences that are generated from a transcriptome assembly. And these graphs, again, as we've been mentioning, are helpful for us because they can help us obtain information on the graph assembly, such as we've been mentioning, i.e. the number of nodes, the total number of base pairs in the sequence, the degrees of each one of the nodes, and the like. And we provided a few examples out of hundreds of thousands of possible graphs from the two FASTA files that we've been talking about, one of which has a total number of base pairs of approximately 7.8 million, and the other one has approximately, I think, 65 million or 68 million base pairs that we've been mentioning. And as a concluding point, many additional opportunities remain, either for other RNA sequencing data sets or other data sets that one can use in tandem with assembly procedure pipelines. And thanks for watching.